augmented negative sampling for collaborative filtering. And Johan will present an analysis of the challenges of state-of-the-art negative sampling techniques for collaborative filtering based on implicit feedback, and propose an augmented negative sampling strategy to address these challenges.
Thanks for your introduction. Good morning, everyone. My name is Yuhan Zhao. Today, I will show you our new work, Augmented Negative Sampling for Collaborative Filtering. The structure can be divided into 5 parts: backgrounds, related work, motivation, method, and experiments. So, collaborative filtering as an important paradigm of recommender system leverages observed user-item interactions to model user preferences. In real world, such interactions are normally in the form of implicit feedback. For example, click or purchase. Well, in implicit feedback, each observed interaction is regarded as a positive sample, and the negative sample is selected from the uninteracted items, which cause negative sampling. Recently, studies have shown that negative samples have a great impact on model performance. That's why our research focuses on negative sampling strategy. So far, about 2 lines of negative sampling methods have been proposed. The first is model-agnostic negative sampling. Such strategies are normally efficient since it does not need to be adjusted in the training. For example, RNS randomly select items from interactive items, uniform distribution. And the other is model-aware negative sampling. This strategy takes into consideration some information of the model. The most famous work is hard negative sampling. It assigns higher sampling probability to negative items with larger prediction scores. For example, DNS. So ideally, model-aware negative sampling would calculate the scores of all uninteracted items to identify the best negative sample. However, its time complexity is prohibitive. To balance efficiency and effectiveness, the two-pass approach have been well adopted. So the first pass samples a fixed number of unobserved items by a simple static distribution. You can see we get M candidate items. And then the second pass selects the final negative items with more complex negative sampling strategies. You can imagine the first pass is model agnostic, and the second pass is model aware. In this paper, we reveal 2 notable limitations in existing studies. First, we call the ambiguous trap. Majority of unobserved items have very low scores. So randomly sampling a small number of candidate negative items in the first pass is difficult to include hard negative samples. To verify this point, we choose MF as a base model and calculate the scores of all unobserved item score in different training periods. The lowest 80% of the scores are highlighted by the pink shade. You can see in epoch 30 and epoch 50, most of items have very low score items, and just a few items have high score. So it is difficult to select the high score items with a simple and static distribution. And another question is information discrimination. In the second pass, most existing studies focus on high score negative items and overlook low score negative items. We think low score negative items also contain critical unique information. To verify this point, we introduce a PER heat map. You can see in figure A, the RNS row DNS column. It means RNS have 20% unique information that DNS cannot learn. So recall RNS randomly select items. That means RNS equal low score item. These experiments show that low score items also have unique information. Our response to such limitation is to introduce augmented negative symbols that are more similar to positive, will still be negative. We propose a novel generic augmented negative sampling paradigm. The paradigm have three major steps: disentanglement, augmentation, and sampling. The disentanglement step learns the item hard and easy factor in a fine granular perspective. You can see we divide the original embedding to easy factor and hard factor. Then augmentation is just on the easy factor. You know, hard factor means it's hard enough. Then we have a sampling strategy. We introduce a new metric called augmentation gene to alleviate the information discrimination we talked before. Note that these steps can be implemented by different methods, and thus the overall paradigm is generic. You can replace any steps by your own methods. So first, we disentangle item embedding into hard and easy factors. You know, a set of dimensions of the embedding vector. Well, hardness is defined by whether a negative item have a similar value to the user. You can see equation 3 and equation 4. We design a git method. Then we adopt a similar operation with a positive item. This is particularly important as hard factor may highlight the first 48 dimensions, while easy factor may highlight the last 40. So it is important to keep the alignment of the dimension. We find we have a big challenge that we don't have any labels or supervised signals to guard how to disentangle, and so it is difficult to guarantee the credibility of the disentanglement. So we introduce contrastive learning. We design contrastive laws. By definition, the hard factor of a negative item should be more similar to the user, while the easy factor should be opposite. So we design the equation 5. And the disentanglement laws, intuitively, hard factor should be more similar to positive, since it is difficult for user to discern it as a negative symbol. Both of them have a high similarity to user, so we believe they also have high similarity. Then we talk about augmentation. Our goal is to augment the easy factor to improve model performance. We propose to regulate the augmentation from two different aspects. First, direction. Intuitively, the direction of augmentation on a negative item should be towards the positive one, because positive, you know, have a high score with user. And then we design the magnitude. First, we generate a noise data from a uniform distribution, and we restrict the data smaller than a margin. The margin can be calculated by equation 10. The intuition is that a higher similarity between the hard factors suggests that the negative item already contains much useful information. So thus, we should augment it with a smaller magnitude. However, as explained before, negative items with low scores will be seldom selected, which leads to the information discrimination problem. We design a sampling strategy by introducing a new metric named augmentation gain. So the augmentation gain is calculated by the score difference before and after augmentation. We considered both score and the augmentation gene to select the suitable negative item by equation 30. Finally, we adopted the proposed ANS methods as a negative sampling strategy and use loss error to optimize our model parameters. ANS can be seamlessly incorporated into mainstream models without any modification. This slide shows our performance compared with other baseline. You can see we got the best performance on almost data size. And this table shows different base model with our ANS or without our ANS. From these two tables, we can see ANS shows the best performance on almost all data size. And then the ANS adaptability is a noteworthy feature that ANS can be incorporated into mainstream model. Despite its simplicity, DNS is a strong baseline. This factor justifies our motivation of studying the hardness. Then we talk about our distinguishment performance. We project our embedding, use TSNE into two-dimension space and analyze. So we can see NE denote negative hard factor, NH negative hard, PE positive easy, pH positive hard. The hard factor are cluster because they are indeed similar with user, so they carry similar information. The easy factor are scatter because they carry different information and the information is not important. Then we see how NS alleviate our problems. So we show the curves of recall. In the beginning, ANS have shown the worst performance because ANS need extra effort to learn how to disentangle and how to augment. And subsequently, ANS has a greater gradient. That means ANS can bring more information by the harder negative samples. And table 4 shows the percentage of the overlapping high score items between DNS and ANS. Recall, DNS means high score items. Our ANS only have 50% overlapping item, means ANS tends to select more low score items. So we can alleviate the information discrimination. Then follow the previous work, we analyze the efficiency of ANS. It can be said ANS methods require more running time. However, considering our huge performance improvement, the additional running time is well justified. So finally, it's our summary. We designed a set of intuitive experiments to reveal two notable limitations. And we are the first to propose to generate negative samples from a fine granular perspective to improve implicit CF. We proposed a general paradigm called ANS, and we conduct extensive experiments to show our performance. That's all. Thank you for listening.
Thank you very much, Johan. Can you hear me okay, or should I come over there in case? Can you hear me okay? Okay. Yeah? Are there any questions from the audience here or on Slido? I don't see any questions on Slido yet. If not, then I'll start with one. So one of the questions I had when reading the paper was about what that third augmentation step, the sampling step, right? What that contributes to performance compared to existing negative sampling methods. You do this ablation study where you look at all the individual components and what they contribute, but the difference between your combined ANS approach and the one without that last sampling, where you also include the augmented scores, right? That wasn't, that was the smallest of all the differences. And it's not clear that that difference was even significant. So can you say a bit more about how much the sampling contributes, that last step?
Actually, we do a more comprehensive experiments in our paper, but due to the time limitation, we don't show this section. So if you are interested, you can see our original paper.
I'm talking about the ones in the paper, right? The difference between with and without that sampling wasn't so big, and it wasn't clear whether this was significant. So does the sampling really, yeah. This one. Oh, sorry.
Yeah, this is a good question, and maybe we can show in the slide. So before our argumentation, actually our all negative samples have similar scores. So just use the traditional sampling strategy. Also can select some low score items which contain unique information. But we additional design augmentation gen to keep to be a more intuitively way to achieve this goal. Yeah, this is my answer.
Okay, thanks. There is a question online. How do we decompose embeddings into easy and hard parts?
Yeah, we design a gate method. You can see we use a gate to do a Hadam product to get some dimensions, and we design two additional loss function to regulate the disentanglement part. So if you want to disentanglement, you can replace this method by your own methods. It's just our implement.
No more questions from the audience online or here. Then I have one. Could you put the slides back up? Can you go back a few slides? Yeah, two forward. One more.
One more.
Why does it take ANS about 30 epochs before it actually shoots up? Before it shoots up? Why does it take ANS so long before it starts?
0 to 30?
Yeah.
This is a good question because our ANS need more epoch to train our disentanglement and augmentation parts. You know, it's a neutral network, so it needs extra epoch to train. That's why in the beginning we got the worst performance.
Okay. Okay, if there are no more questions, then let's thank Johan again.